The Casimir Effect. The starting premise is simple. What happens when you keep two uncharged conducting plates near each other? But before that, we need to understand a few things. We are going to model our field by a real scalar field. What exactly is a field? A field is a quantity at every point on a manifold. The quantities can include things like charge density, temperature, etc. And the manifold is often space or spacetime. The field that we are going to consider is a real scalar field over spacetime, which evolves with the following equation called the Klein-Gordon equation. As the name suggests, this is a field of real numbers, and we see that the field has infinite degrees of freedom, one at each point in space. Now, if we look at the Fourier decomposition of the field and substitute it into the Klein-Gordon equation, we get that the degrees of freedom decouple and at each point evolve independently as a simple harmonic oscillator with the frequency omega p. So far, what we have considered is a classical field. Now, turning this classical theory into a quantum theory and defining the vacuum to be a state where no particles are present, we get the expression for the energy of the vacuum to be this. I'm not going to show you how we arrive at this expression, but we can see that the expression is not so far-fetched and we can get some intuition along the way. Now, if you know a little quantum mechanics, you will know that the lowest possible energy of a simple harmonic oscillator is 1 by 2 h bar omega. Since the field is a linear combination of infinite simple harmonic oscillators, it's not completely shocking that the energy is as well, and it is given by the following expression. But we see that there is a problem with this expression. It diverges to infinity. Now, how are we going to deal with this infinity exactly? The integral, in fact, diverges in two ways, termed as infrared divergence and ultraviolet divergence. Firstly, we are going to talk about the infrared divergences. We will see that this divergence actually arises from the infinite extent of space, which is manifested in the delta function. The delta function can be written as now. Let's decrease the size of the universe and put it in a box of side length L. As a result, the limits of the delta function now range from minus L by 2 to L by 2, and the delta of 0 becomes. We see that the delta function now becomes V over 2 pi cubed, where V represents the volume of the box, i.e., the universe. Substituting this expression we got for the delta function into the expression for energy. So, energy density is more of a reasonable quantity to observe than the energy of the vacuum in its entirety. But we still see that the integral diverges to infinity, since we let the momentum go to infinity. It is clearly absurd to think that our theory will be valid for arbitrarily low wavelengths. This is the origin of ultraviolet divergence. All theories fail at a certain wavelength. Classical mechanics fails at the Compton scale, and quantum mechanics fails at the Planck scale. We would assume that our theory is also not valid after some momentum, so we introduce a cutoff wavelength. With a limit on the momentum, we finally get a finite energy density. With this, we have made sense of the infinities that arise in the energy of quantum mechanics. But there is another way of dealing with the infinity that arises. We argue that in physics, it is the energy differences that matter and not the energy. And the energies that we measure are also energy differences. So we set the energy of vacuum to be zero. And this works. Or does it? We see that the infinity of the vacuum energy does manifest itself in certain cases. We are going to look at one of the cases. Let's revisit the premise of the Casimir effect. Now that we know some things, we have two reflecting infinite plane sheets separated by a distance d, and the real scalar field whose existence permeates all space. The plates impose a boundary condition that the field phi on its surface is zero. Now, to regulate the infinity, we are going to assume that the whole universe sits in a box of length L, which is far greater than the separation between the plates. And at the end of our calculation, we tend L to infinity and hope we get the right answer to our physical problem. We impose periodic boundary conditions on the boundaries of the box, but only in the x direction, because we are interested in the differential of energy with respect to d, which is along the x direction. Because of the boundary conditions at the plate, the Fourier decomposition of the field is affected, and only the possible modes are present. Because of the periodic boundary conditions, the Fourier decomposition outside is also affected, but with a different fundamental frequency. As we saw previously, the energy density is given by. Also, another assumption that we need to make is that our field is massless. For the massless field we are considering, it is given by. From now on, I'm going to be using natural units in which h bar and c have the value of 1. This will make our calculations a lot neater. Inside the plates, the value of px is quantized, and so the possible values of p are the possible modes in the space outside can be obtained by replacing d with L minus d. Due to this, the quantity of interest becomes the energy per unit area in the zy plane, and it is given by. But wait, we still haven't taken care of the UV divergence, so the integral still tends to infinity. We can take care of that by regulating the integral with an exponential function, because of which the contribution due to high momentum become irrelevant, and at the very end we are going to let a tend to 0. We can physically interpret this cutoff. Metal sheets start becoming transparent to photons as their wavelength decreases. Similarly, in our case, we assume that the plates or sheets become non-reflecting for the high frequency modes. Now, we can see that the total energy of our system is. Differentiating with respect to d, we can naively see that there can indeed be a force, or more precisely, a pressure between the two plates. The calculation for the case mentioned above is non-trivial, so we are going to look at the easier calculations of a field in one space and one time dimension. The energy between the plates is now given by. This clearly diverges. Regulating the function with an exponential and solving it, we get. Now, adding the energies inside and outside, we get the following. Taking its derivative and taking the limit a tends to 0 and L tends to infinity. So, we get a finite force even after removing our regulators. This is the now doing analogous calculations for the 3 plus 1 dimensional case, we get the following result. This is the Casimir pressure. In reality, we can observe the effect by placing conducting plates near each other, and the field responsible for this is the electric field. Also, in this case, the pressure is twice of what we calculated because of the different polarization states of the photons.